For decades, the familiar clickety-clack of train wheels rolling over expansion joints was a soundtrack to rail travel. This rhythmic sound, while nostalgic for many, was actually a byproduct of an older technology that had its own set of challenges and limitations. These joints, small gaps between sections of rail, were deemed essential to accommodate the expansion and contraction of steel with temperature changes. They allowed the rails to expand in the heat of summer and contract in the cold of winter without causing the tracks to buckle or break. However, a revolutionary technology emerged, forever changing the face of railway's continuous welded rail, or CWR. This innovation was not just a minor tweak, but a significant leap forward in railway engineering. CWR, as the name suggests, eliminates the need for expansion joints by welding rails together into long, unbroken stretches. This process involves using high-temperature welding techniques to fuse the rail sections, creating a seamless and continuous track. Imagine a single rail snaking its way for miles, uninterrupted and seamless. This continuous stretch of rail not only looks impressive but also functions far more efficiently than traditional tracks. This seemingly simple change brings a plethora of benefits. The most immediate advantage is a smoother, quieter ride for passengers. Without the constant clattering over joints, the journey becomes more serene and pleasant. The most immediate advantage is a smoother, quieter ride for passengers. Gone are the rhythmic thuds and vibrations caused by expansion joints. This translates to a more comfortable and enjoyable journey, free from the jarring discomforts of old. Gone are the rhythmic thuds and vibrations caused by expansion joints. This translates to a more comfortable and enjoyable journey, free from the jarring discomforts of old. Passengers can now enjoy a ride that feels almost like gliding, with minimal noise and disturbance. This translates to a more comfortable and enjoyable journey, free from the jarring discomforts of old. But the benefits extend far beyond passenger comfort. The smoother ride also means less wear and tear on the train's components. But the benefits extend far beyond passenger comfort. CWR significantly reduces wear and tear on both the tracks and the trains. The absence of joints means less impact and vibration, leading to a longer lifespan for wheels, axles, and other critical components. CWR significantly reduces wear and tear on both the tracks and the trains. The absence of joints means less impact and vibration, leading to a longer lifespan for wheels, axles, and other critical components. This reduction in wear and tear translates to substantial cost savings for railway operators. The absence of joints means less impact and vibration, leading to a longer lifespan for wheels, axles, and other critical components. This reduction in wear and tear translates to substantial cost savings for railway operators. Maintenance requirements decrease, and the lifespan of both rolling stock and the track itself is significantly extended. This reduction in wear and tear translates to substantial cost savings for railway operators. Maintenance requirements decrease, and the lifespan of both rolling stock and the track itself is significantly extended. The economic benefits are clear, but there are also environmental advantages. Maintenance requirements decrease, and the lifespan of both rolling stock and the track itself is significantly extended. With fewer repairs needed, there is less disruption to services and a more reliable schedule for passengers. Additionally, the environmental impact is reduced due to fewer materials and resources being used for maintenance. CWR is a testament to the fact that innovation can go hand in hand with efficiency and economic viability. It represents a forward-thinking approach to railway engineering, one that prioritizes both performance and sustainability. As we continue to advance, technologies like CWR will play a crucial role in shaping the future of rail travel. If you enjoyed this video, don't forget to subscribe, like, and share Cosmo Academia for more fascinating insights into the world of science and technology.
Subscribe, like, and share Cosmo Academia. The process of joining two rails together to form a continuous welded rail is a marvel of engineering precision. This intricate procedure ensures that trains can travel smoothly and safely over long distances without the disruptions caused by traditional rail joints. It all begins with aligning two rails precisely end to end. This alignment is critical because even the slightest misalignment can lead to significant issues down the line, including potential derailments or increased wear and tear on the train wheels and tracks. These rails, often weighing several tons each, are carefully positioned using specialized equipment to ensure a perfect match. The machinery used is designed to handle the immense weight and length of the rails, making sure they are perfectly aligned before the welding process begins. Once aligned, the ends of the rails are heated to a scorching temperature. This heating process is essential as it prepares the metal for welding, making it more malleable and ready to bond. This is where the magic happens. The welding process involves using a combination of heat and pressure to fuse the rail ends together, creating a seamless and strong joint. The extreme heat alters the very structure of the steel, bringing it to a semi-molten state, where it becomes soft and pliable. This state is crucial for the welding process, as it allows the metal to flow and merge seamlessly. With the rail ends glowing red-hot, a powerful hydraulic system presses them together with immense force. This pressure ensures that the two pieces of steel are not just touching, but are actually fused at a molecular level. This pressure, combined with the intense heat, fuses the two pieces of steel into a single monolithic unit. The result is a continuous rail that is as strong, if not stronger, than the original pieces. The molten metal intermingles at the interface, creating a bond as strong as the rail itself. This bond is what allows trains to travel smoothly over the welded joint without any noticeable bumps or disruptions. However, the process doesn't end there. The newly welded joint must undergo a cooling process to solidify the bond and ensure the rail retains its structural integrity. The newly formed joint needs to cool down, but not just at any rate. The cooling process must be carefully controlled to prevent any weaknesses or defects from forming in the metal. Rapid cooling is crucial to ensure the steel retains its strength and structural integrity, a process we'll delve deeper into in the next section. This step is vital for the longevity and durability of the rail, ensuring it can withstand the heavy loads and stresses of passing trains.
The intense heat used in welding rails alters the crystalline structure of the steel, making it more ductile and easier to fuse. However, allowing the steel to cool slowly can have detrimental effects on its strength and brittleness. When steel cools slowly, large crystals form within its structure. These large crystals create weak points that can lead to cracks and fractures under the immense stress of train traffic. To prevent this, a process called rapid cooling is employed. Immediately after the rails are joined, they are sprayed with a jet of high-pressure water. This rapid cooling freezes the steel's structure, preventing the formation of large crystals. Instead, a fine-grained structure with increased strength and toughness is achieved. The result is a welded joint that is as strong, if not stronger, than the surrounding rail. This rapid cooling process is essential to ensure the long-term durability and safety of continuous welded rail.
Section 4. Thermite's fiery dance. A spectacle of heat and fusion. The extreme temperatures required to weld rails necessitate a powerful and reliable heat source. Traditional methods often fall short, unable to generate the intense heat needed for a seamless and durable weld. This is where the brilliance of thermite welding comes into play. This is where the thermite reaction takes center stage, a pyrotechnic spectacle that is as visually impressive as it is effective. The reaction itself is a marvel of chemistry, producing temperatures that can exceed 2,500 degrees Celsius, enough to melt steel effortlessly. Thermite is a mixture of aluminum powder and iron oxide or rust. When these two components are combined, they form a highly reactive mixture that, when ignited, produces an intense exothermic reaction. When ignited, it undergoes a highly exothermic reaction, releasing an enormous amount of heat, enough to raise the temperature of the surrounding steel to its melting point. This reaction is not only powerful, but also incredibly efficient, making it ideal for welding rail tracks. To control this fiery process, the thermite mixture is placed in a refractory crucible positioned above the rail joint. The crucible is designed to withstand the extreme temperatures generated by the reaction, ensuring that the molten steel flows precisely where it is needed. The reaction is triggered, and molten steel, heated to over 2,500 degrees Celsius, pours down into a mold surrounding the joint. This molten steel fills the gap between the rail ends, creating a strong and seamless bond as it cools and solidifies. These molds, often made of ceramic or sand, are designed to withstand the intense heat. They play a crucial role in shaping the molten steel and ensuring that it forms a perfect joint. Importantly, they are often made with see-through sections, allowing workers to monitor the flow of molten steel and ensure a complete and uniform weld. This transparency is vital for quality control, as it allows for real-time adjustments to be made if necessary, ensuring the highest standards of safety and durability.
Subscribe, like and share Cosmo Academia. Section 5. The Metal Masterminds. Metallurgy's role in rail welding. Behind the scenes of the impressive welding process lies the critical role of metallurgy. Metallurgists are the unsung heroes of rail welding, ensuring the steel used possesses the necessary properties to withstand the demands placed upon it. The composition of the steel is crucial. The addition of elements like carbon, manganese, and silicon influences the steel's hardness, strength, and weldability. Metallurgists carefully control these additions to create a steel alloy specifically designed for rail applications. Furthermore, they analyze the microstructure of the steel after welding. Using sophisticated techniques like microscopy, they examine the size and distribution of grains, ensuring the rapid cooling process has produced the desired fine-grained structure. This meticulous attention to detail ensures that the welded rails possess the necessary strength, toughness, and durability to withstand decades of heavy train traffic. The science of metallurgy is the invisible force that underpins the success of continuous welded rail.